In this computer session, we are going to spatially vary a planar grating. And interestingly, probably 80 to 90% of everything involved in generating spatially variant lattices will be tied into this code, generating spatially variant gratings. It's all based on that. So we're going to write a short, pretty simple code, and we will definitely be spatially varying a grating. So the first thing, we need to define some properties of the planar grating. So later on we'll define the angle and everything. So let's just define the nominal period of the grating. And that'll just be 1. And we can still spatially vary that. We'll just vary it about that value. Like before, we'll need some grid parameters so we know how many points, how large the overall grating will be. So the first one will be the physical width of the grid. And we'll stick with the 10 number of periods. That looks pretty good, and it still calculates pretty fast. So we'll stick with that. Next, we're going to define 2 different resolution parameters. Before we defined that nres, now we're going to have an nres low, and we'll set it to something like 4, and an nres high we'll set to something like 10. And we can play with these later. What we'll find from the theory lectures is that when we calculate the grating phase, we see that the spatially variant parameters, the grating phase, they're all very slowly varying around the lattice. It's not until we generate the grating of the lattice that things start to vary very, very abruptly. And when they vary abruptly, we need a pretty fine grid to resolve that. But it doesn't make sense to do everything else on that very fine grid. So what we'll do is we'll define 2 grids. One that's low resolution that will do most of the work, and we'll get all the way up to the grating phase, and then we interpolate that to the high resolution grid and construct our grating. So we have an nres low and an nres high. And in this case, both are the number of points per period. And it just gives us the opportunity to be a little bit more efficient. So that's it for the dashboard here. Let's go on to the next step. We have to calculate all of the other parameters of these grids. So we'll call this section of code Calculate Grids. The first one is the low resolution grid. And we'll use many of the techniques that we used in the last computer session. But we'll start off by the cell size is the period of the grating divided by that the nres low parameter. And we'll do the same thing for dy, a over nres low. That gives us sort of a first guess as to the cell size, and that's how we define the nres low, number of points per period. Next, we'll calculate how many points on the grid, and we'll round up of big Sx over little dx. So we're dividing the physical width by the width of our cell, and that gives us a number of points. Now, if that ratio were an integer, we've rounded up. So in fact, it makes sense to recalculate dx then. And we'll do the same exact thing for ny. Okay. And if we run it, we shouldn't get any errors. Close that figure window. Our low resolution grid will be 40 by 40 points. Clearly that will process pretty darn quick. Now we'll need those axis vectors that tells us the positions of the points running horizontally and vertically. So we have xa, nothing there should surprise us, and I'll center it about 0 and do the same thing for ya. I'll run it just to make sure I get no errors. No errors. And then the last step is to generate the mesh grid. And we're ready to go. That finishes up calculating all the parameters of the low resolution grid. We need to do a very similar thing now, but for the high resolution grid. We're covering the same physical space as the low resolution grid, but just now with more points. So let's calculate the resolution. We'll calculate it the same way we did before, A over, but in this case, NRes high. So dx2, we put the 2 there to represent that this is the high resolution grid. We'll calculate dy the same way. And we'll calculate the number of points as the physical width divided by the cell size, and we round up. From here, we'll do things a little bit differently. We need to interpolate from one grid to the other. We don't like to have points on one grid that are outside of the other grid. That makes the interpolation a little bit more difficult. Not impossible, and MATLAB does make that pretty easy, but we're going to avoid doing that here. And the way that we can do that is to define our axis vectors for this high resolution grid this way. We'll use the linspace command, and we'll start it at the same point that the low resolution grid starts, and we'll end it at the same point that the low resolution grid ends. But we'll do it with nx2 points instead of nx. Now that'll require us to recalculate the grid resolution parameter. So we'll just say xa2, say 2, 1. So the second number minus the first number gives us the spacing between them. We'll do this exact same thing for the y-axis. We'll start it at the same point as the low resolution y-axis. We'll end it at the same end point as the low resolution, but we'll do it with big ny2 points. And then recalculate the grid resolution in the y direction. And we'll also do a mesh grid for the high resolution grid. And that's it for our grids. We'll run it to make sure we don't have any errors. And looks like no errors. That's still not a 100% guarantee things are correct, but we'll find out later if it doesn't work whether these were correct or not. Now we're going to spatially vary a planar grating. We need at least 3 inputs to tell us how to spatially vary it. We need to spatially vary its period, its orientation, and its fill fraction or fill factor. So we need to define arrays that define how we want to spatially vary these. So we'll name this section Generate Input Data. So let's do something interesting with period. We're saying period x minus y, and we'll see what that does in a minute, but that gives us some picture. What we want to do is subtract the minimum value and then divide by the maximum value. Now that will limit this period array to go between 0 and 1. And then we'll scale it this way. Now let's look at it. Let's draw this. So we have 3 things that we want to draw, and later on we're going to be drawing even more things. So we'll do a subplot 2, 3, 1, which means our subplot will be 2 plots deep, 3 plots wide, and right now we want to plot to the first one of those. As long as those are single digits, MATLAB doesn't require you to put commas between those numbers, but we certainly could. Now rather than p-color, I like to use the image_sc command. It's a more intimate tie to how the data actually looks in your arrays. It shows the pixelation. p-color does some other things. p-color is great for generating nice, smooth, high-quality pictures for publications, but when I want to visualize my data, I like using image_sc a lot. But there are some problems with it. Image_sc thinks it's drawing a matrix, and so the positive z direction is down instead of up, but we can fix that. we will get a handle to that image SC. Then we will get its parent. So the handle that comes from image SC is really a handle to the period data. When we get its parent, it comes one level up. Now we're looking at the axes and the properties of the diagram that we're drawing. And we'll go in there and we'll change the property of y direction to normal. It defaults to reverse. And that way it'll make positive z in the upward direction. So it's a little bit more intuitive for us. We'll give it a color bar so we can see the dimensions. You'll see the number values associated with the colors. Axis equal tight for reasons we discussed in the last computer session. And we'll give it a title. This is PER. Now if we run it, we should see what we've done for period. Notice the period now is going from 0.5 in the upper left corner down to 1.5 in the lower right corner. So we're chirping the period of the grading along the diagonal. All right, we need more input arguments. Next, let's define the orientation, this theta parameter. And let's make it a circle, or a smooth sort of Gaussian function in the middle. So what we'll do is we'll orient the grading in a circular region in the middle of the grid, different than how we orient it at the outside of the grid. And so we'll make the radius of this maybe a quarter of the physical width. I'm going to calculate a radius squared using my mesh grid variables. So if I were to plot r squared, let's just do it and we'll see it. Color y q equal tight color bar. We'll look at what RSQ is. So it is a radius function with 0 at the middle and numbers increasing outward. And the value at each point is its distance from the middle. So I like to do this for creating circles. So we have our radius squared function. And now let's make theta. Let's put it 45 degrees inside that circle in the middle of the grid. Alright, that should do it. And let's draw it to the screen so we can see what we've just done. We'll go to the next subplot. Display theta. Okay, let's take a look at it. So we have a value of 0 on the outside, meaning we want our grading to be vertical on the outside. And on the inside, it's 45 degrees, so our grading will be tilted at 45 degrees in the circle, yet vertical outside, and somehow this algorithm has to figure out how to make all the lines straight, continuous, and defect-free. But we don't have to worry about that. The algorithm does that for us. Then the last thing is the fill factor. And we'll do something strange for that too. And by the way, there's nothing magical about what I'm doing, how I'm defining the period and angle and fill factor. I'm just coming up with easy to come up with random arbitrary patterns. It really could do anything. I've even loaded in bitmap images and spatially varied things according to pictures. Okay, so fill factor will be a 2D array of the fill factor we want our grading to be. Now the fill factor, we're designing on this high resolution grid. Remember, we go through and calculate all the way up to grading phase, interpolate that to the high resolution grid, construct the grading, and then control fill fraction. So fill fraction is done on this high resolution grid, so we're using the x2 and y2 mesh grid parameters. Then we'll do the same thing again. We'll scale it between 0 and 1. That will scale it between 0 and 1, and then that makes it easier to scale how we want to. So we'll just say it goes between 0.2 and 0.8. And I said 0.8 because When FF is 1, we got a 0.6 added to a 0.2. So basically FF will vary between 0.2 and 0.8. And when we draw it, that'll make sense. So let's go ahead and visualize it. So fill fraction, we'll do it to the third subplot. FF, and we'll label it FF. Okay, let's run it now. And now we have fill fraction being chirped from a value of 0.2 to 0.8 along another diagonal, the opposite diagonal that we did for period. So we're doing a bunch of crazy stuff here, and we really could do anything. I just made those up because they were easy and quick to do. So that finishes that step. We have now defined all of the input arguments to our algorithm that will spatially vary the planar grading according to those inputs. And now the magical part, the actual algorithm to generate the spatially variant grading. So that's next. Okay. So the algorithm begins by constructing the k function. And this is a map of our k vector across the grid. And it has a magnitude 2 pi divided by the period, but now period is a two-dimensional array because we're spatially varying the period. So we have to say dot divided by period. We now have the magnitude of kx and ky across the grid. And we also need to get the orientation in there. So the k function only has period and orientation data. The fill factor comes last. ky is defined the same way, but with a sine theta. PER and theta are both two-dimensional arrays that we just constructed. So we now have our spatially variant k function. We know that we're going to calculate the grading phase using the finite difference method, solving del phi equals k. So we need some derivative operators. And you were provided a function. SVL dir. And we give it the size and resolution of the grid. So ns is nx and ny. That's the size of our grid, the low resolution grid. And we have dx and dy are the resolution parameters on that grid. And I don't know why I like to align the equal signs. Okay, so that constructs our derivative operators for that grid. Let's just go ahead and run it, make sure we don't have any errors. Okay, no errors. And by the way, if we're curious what dx and dy look like, let's make sure they're not too big to visualize. Not bad. All right, so let's just look at one. So notice it's all zeros except we have some numbers running down the middle. It's a banded matrix, and it is performing our derivative operation. It calculates the derivative of phi to give us kx or ky. So again, we're not discussing theory here. It's just interesting to look at some of these things. Now the big step. Solve for grading phase. This is where we solve that least squares problem. So we build our matrix A. This is the gradient operation. So it's dx riding over top of dy. B is our grading vector. So it, by this command, takes this two-dimensional array kx and stretches it out or reshapes it to a one-dimensional array and makes it a column vector. So we have kx right over top of ky that we also stretch out to a column vector. Now we could at this point just say A backward divide B. MATLAB would yell at us, but it would solve it anyway. But technically it's solved in the sense of least squares. So let's go ahead and just do this explicitly. And what we would do to A is pre-multiply it by its transpose, and then we backward divide B, but we also pre-multiply that by the transpose of A. So that one line solves for the grading phase in the sense of least squares. But phi comes out being a two-dimensional array, so we need to reshape it. I'm sorry, phi comes out being a one-dimensional array. It's a column vector. We need to reshape it to the two-dimensional array. And it's on the 1x, or the low resolution grid. Let's take a look at it. Let's run it, make sure there's no errors. Okay. And let's take a look at our grading phase. Now we'll use P color for it. And that's kind of interesting. We see it's doing a wiggle. And remember, that's because our planar grading is oriented at 45 degrees in the middle. And we can think of the grading phase as the phase of a wave, and we can almost imagine it propagating from the dark blue to the dark red and progressing in directions, you know, normal to the color interfaces, if you will. So that's what our grading phase looks like. So we did a lot of work, and this was the big step. We did all this work on the low resolution grid. Now what we want to do is interpolate that up to the high resolution grid. We use the interp2 command for that. We give it our two axis vectors. We give it the original phi, and now we give it the new axis vectors. These are the ones on the high resolution grid. And if we were to run this, and let's look at the grading phase, we'll use the P color command, but since it's on this high resolution grid, we need to use XA2 and YA2. Notice it looks the same, but with twice as many points. Well, actually more than twice as many, with more points. It's on the high resolution grid. Now we want to calculate the analog grading, which is a piece of cake once we have phi. So we use GA for the analog grading. And we just say cosine phi. Let's get a little bit more sophisticated and start showing these things. So let's show the grading phase, and we'll plot this. We'll keep all the things that we already have on our subplot, and now we'll go to the bottom row of our subplot. So that does a P color. It shows our phi. I don't like the black lines, so we'll use a shading interp. We'll give it a color bar so we know what color corresponds to what value. Axis equal tight, so it looks square or whatever shape it is. And we'll give it a title. And that is phi. We've just calculated the analog grading. So let's go ahead and look at this. Show analog grading. We'll go to the next subplot, plot GA, and we'll call this the analog grading. Let's run it. Okay, there's our grading phase, and this is our analog grading. One thing I want to point out, notice what's going on here. It looks a little bit sloppy. We not only have a somewhat low resolution grid here, but we see pretty sharp kinks. And it turns out we can clean this up a little bit by blurring our input data. So we can fix this just by blurring theta. Notice this is kind of staircased. It's on a very low resolution grid. We want that for speed. We could make our low resolution grid higher resolution to fix that, or we could just slightly blur our theta function. Let's try slightly blurring it. So we'll come up to theta. We'll say theta, SVL blur, and then we give it the number of pixels. We'll just do a 2-pixel blur, and let's run it. And notice our theta is blurred, and it has cleaned this up significantly. And we would see even more of a dramatic difference in our binary grading. That's next. But there is our spatially variant grading. And notice it has a small period here, according to our period, and it chirps to longer period down to the lower right. So short period, chirping down to long period. Theta, we have a vertical grading outside of this circle, and it's oriented at an angle inside the circle. And the fill fraction we haven't incorporated yet. That will come into the binary grading. So that's next. Let's do the binary grading. All right. Calculate binary grading. We will use the same trick we had before because our grading has a cosine function. So we can estimate what the threshold value is as pi times the fill fraction, cosine of pi times the fill fraction. And once we have this threshold, this is a two-dimensional array of what the threshold needs to be at each point in our grid, we can calculate the binary grading, simply as the analog grading greater than GTH. And the last thing is let's show the binary grading. And we will go to the next subplot. So that is 2, 3, 6. And the binary grading is digital, and I probably want to get a better look at the staircasing, and that's where the P color command I think just doesn't work as good. So we're going to use ImageSC. And like we did before, we're going to need to change the y-axis direction. So we will get its parent, a handle to its parent, and then we will set the y direction to normal instead of reverse. Reverse is the default for ImageSC because it thinks it's drawing a matrix instead of a picture. Okay, so now we should see a binary grading. Whoops. We were still displaying GA instead of GB. Okay, now we have a binary grading, and you can see how we're chirping the fill fraction. At the upper right has the highest fill fraction, 80%, and it chirps all the way down to 0.2. We can see that chirping happening from the upper right down to the lower left. So this really is our final grading on the lower right, and we've spatially varied 3 different things about it, and we spatially varied each one in a different pattern completely independently, and still the final lattice is smooth, continuous, defect-free. Now what I want to do is I want to play with some things to show how we could break this, or what it does when we push the parameters to the limit. So let's take our NRES parameters way down, 2 and 4. Let's see what happens. Notice how digitated this looks, and the analog grading's horrible, and so this doesn't look real good. But it runs very fast. Now if we want a really fast run with a really good looking grading, we'll keep NRES low small for a fast run and make NRES high for something that looks really good. So we'll keep NRES low to 2 and set NRES high to 40. Let's see what happens. Pretty good. I do notice a little bit of bulging in the lines here, and we can probably take care of that by improving the resolution a little bit on the low resolution grid. But this one's looking pretty, other than those errors, this is looking pretty good. That's almost publication ready. But I would, just to eliminate those bulging artifacts, come up to something like 6 or 8. Let's put in 8. And we see a little bit smoother lines. I don't think it'll get much better than this, but that is something that's nice and smooth. We could mesh that, we could do other things, we could put it in a publication. That's ready to go. So that's it. That is how to spatially vary a planar grating. I would definitely recommend learning what's in this computer session very well. Everything else we do will build on this. This is key what is here.